Welcome back, Design Junkies, to Mechanical Engineering Made Simple. If you enjoy the podcast, show your support with a like, a follow, or a comment.
Thanks for having me back.
Oh, absolutely. So imagine for a second that you just, turn off your kitchen faucet and the pipes behind your wall just suddenly explode, like with the force of a hand grenade, which is a terrifying thought, honestly.
Right. Or picture yourself flying a jet so incredibly fast that the invisible thin air in front of you just instantaneously turns into a solid, impenetrable wall of force, a wall that can literally rip metal apart.
Yeah, that's the sound barrier for you.
Exactly.
Right.
So today we are bringing you into a very special masterclass. We are talking directly to you, the student of the physical world. And our mission today is ambitious, but I promise it is going to be incredibly rewarding.
It's going to be a fun one.
We are going to build a comprehensive mental model of fluid dynamics from the absolute ground up.
We're talking compressible gases at supersonic speeds, then moving into the erratic nature of unsteady liquid flows. Right, and finally arriving at the cutting-edge computer simulations that allow us to actually see and predict all of this chaos.
It really is a profound journey. When you look at the history of how we understand fluids, which, by the way, means anything that flows, liquids or gases, you realize that for a long time we were just kind of guessing.
Just trial and error?
Exactly. And we're going to trace the path of how we stopped guessing and started manipulating the very fabric of pressure and temperature to do things like, well, go to the moon.
Yeah, you really can't appreciate why we need to build multi-million-dollar supercomputers to simulate like a simple splash of water until you first understand the sheer mathematical headache of supersonic gas.
Oh, it's a massive headache.
I love that framing. So let's start at the very beginning. Let's talk about the fundamental nature of the stuff we are moving around.
The fluids themselves.
Right. When we talk about fluids in engineering, we're usually categorizing them based on one major physical property, which is how they handle being squeezed. I always thought of water and air as fundamentally different things, but mechanically, they're both just fluids, right?
That is the perfect starting point. Yes, both are fluids, but they sit on opposite sides of a very important line, which is compressibility.
Okay.
We define fluids broadly as either compressible or incompressible. Let's look at liquids first, like water or hydraulic oil. For almost all engineering purposes, liquids are treated as completely incompressible.
So if I take like a plastic medical syringe, fill it entirely with water, put my thumb over the opening and push down on the plunger as hard as I can.
The plunger doesn't move.
It doesn't budge at all.
Right. I mean, it barely yields on a microscopic level, but practically speaking, it does not move.
The density of that water, the amount of mass packed into that specific volume, remains essentially constant regardless of how much pressure your thumb is applying.
Because the molecules are already packed closely together. Exactly. Gases, however, are a completely different story. They are highly compressible because the molecules have vast amounts of empty space between them.
So if you empty that same syringe, fill it with air, cap it, and push,
You can easily compress that volume of air down to a fraction of its original size.
you're forcing those air molecules closer together, increasing the density, like squeezing a massive volume of atmospheric air into a thick aluminum scuba tank.
Precisely. But there is a massive caveat to this rule, and it's actually one of the most useful shortcuts in all of fluid mechanics.
Oh, I love a good shortcut. What is it?
Even though gas is highly compressible, we can actually treat it mathematically as if it were an incompressible liquid, provided the conditions are right.
Wait, really? How can we just ignore the fact that air squishes?
It all depends on how fast the air is moving relative to the speed of sound. If a gas is moving slowly, specifically below Mach 0.3, which is roughly 230 miles per hour, the change in its density as it flows over an object is remarkably tiny.
How tiny are we talking?
It's actually less than 5%.
Oh, wow. And in the grand scheme of designing, say, an air conditioning duct, a 5% change in density just doesn't matter enough to complicate the math.
Exactly. For practical everyday calculations, a 5% density change is totally negligible. So the air blowing out of the desk fan in your office behaves, mathematically speaking, almost exactly like water flowing through a wide pipe.
That's wild. The equations are literally the same.
They are. It is only when we start pushing gas to extreme high velocities or dealing with massive altitude and pressure changes that we cross a threshold.
And suddenly that compressibility cannot be ignored.
Right. The air stops acting like water and starts acting like a highly volatile spring.
Okay, so when we cross that threshold, when we start dealing with air moving at hundreds of miles an hour, we have to rely on foundational thermodynamics, right?
We do.
And the big one, the classic rule that governs all of this, is the perfect gas law.
Yes, the absolute cornerstone of thermodynamics. The relationship where PV equals RT.
Right. Pressure times volume equals the gas constant times temperature. Now, I want to make sure I'm visualizing this correctly rather than just memorizing a formula. What is this law physically telling us about the air?
It tells us that for a perfect gas, these core properties, pressure, volume, and temperature, are inextricably linked in this delicate balancing act.
Let's break it down.
Sure. Pressure is just the physical force of gas molecules bouncing off the walls of a container. Temperature is a measure of how fast those molecules are vibrating and zipping around. And volume is simply the space they have to move in.
So if I take a sealed box of air and I crush it down, decreasing the volume, I am forcing the same number of molecules into a tighter space.
Right, so they're going to hit the walls more often.
Which means the pressure goes up.
Exactly. But the law also dictates that if you compress it and hold the pressure steady somehow, the temperature has to change.
Okay, how so?
If you do work on a gas by compressing it quickly, you're adding energy to the system and the temperature spikes. This is why, the bottom of a bicycle pump gets hot when you're vigorously filling a tire.
Oh yeah, I've totally felt that. That makes total sense. Now, this brings up something really fascinating about how gases actually store heat, right?
Yeah, the specific heats.
Right. Depending on how you hold a gas while you heat it up, it behaves differently. There's specific heat at a constant volume and specific heat at a constant pressure. Why does the container matter so much?
Let's use a thought experiment. Imagine you have a rigid, heavy steel box filled with air. It is sealed completely shut.
Okay, so the volume cannot change.
Exactly. Now, you put a blowtorch to the bottom of that box, you are adding heat energy. Because the box can't expand, every single ounce of that heat energy goes directly into raising the internal energy of the gas.
It makes the molecules vibrate and bounce around faster and faster.
Right, so the temperature rises rapidly. This is heating at a constant volume. We denote that specific heat as C sub V.
Okay, that is straightforward. Heat goes in, temperature goes up.
But now, imagine a different container. Imagine a hollow cylinder with a movable piston sliding inside it, kind of like the cylinder in your car's engine.
Okay, the gas is trapped under the piston.
Yep. If you hold a steady weight on top of the piston, the pressure inside remains constant. Now, apply the blowtorch again.
Well, as the gas heats up, the molecules get energized, they hit the piston harder, and because the piston can move, the gas expands. It pushes the piston upward.
Right. The gas is physically doing mechanical work to push that heavy piston against gravity. It's expending energy to expand.
Oh, I see where this is going.
Because it is spending some of that incoming blowtorch heat to do the physical work of lifting the piston, there is less energy left over to simply raise the temperature of the gas itself.
Oh, wow. So if I want to raise the temperature of the gas in the cylinder by 10 degrees, I have to apply the blowtorch for a much longer time than I did for the rigid steel box.
You have to add more heat. Exactly. The specific heat at a constant pressure, which is C sub P, is always higher than the specific heat at a constant volume, C sub V.
And I saw in the reading that the mathematical difference between those two heat values is really elegant.
It is. C sub P minus C sub V is exactly equal to R, the gas constant. That difference in heat energy is literally a direct measurement of the mechanical work the gas performed during its expansion.
That is an amazing way to visualize the math. So we have pressure, volume, temperature, and heat all dancing together, trading energy back and forth.
The thermodynamic dance, yeah.
But how does this dance dictate something like the speed of sound? I mean, when I think of sound, I just think of noise, someone talking, a dog barking. Physically, what is it?
If we strip away biology and just look at the physics, a sound wave is nothing more than a microscopic disturbance in a fluid. It is a tiny, temporary pressure discontinuity.
Like a ripple.
Yeah. When you speak, your vocal cords push a layer of air molecules. Those molecules bump into their neighbors, transferring their momentum and then bounce back. Those neighbors bump into the next layer, and so on.
It's like a microscopic domino effect.
Exactly. It is a longitudinal wave of compression propagating through the fluid. The actual air molecules don't travel from my mouth to your ear. They just wiggle back and forth in place.
But the wave of pressure travels.
Right. And the velocity at which that specific pressure wave propagates forward is what we call the speed of sound.
And what governs how fast that domino effect can happen? Because I was looking at the equations for this, and it totally upended my assumptions.
What did you assume?
I figured that the speed of sound would depend on how thick or pressurized the air is, like denser air, faster sound, but it doesn't.
It does not. The propagation velocity of a sound wave, usually denoted as a, is calculated by taking the square root of k times r times t.
Okay, let's break that down.
K is a specific ratio of heats, r is the gas constant, and T is the absolute temperature. Now, for a given gas, like the air we breathe, K and R are fixed numbers. They just don't change.
Which means the only variable left in the equation is T temperature.
That is the beautiful, isolating truth of it. The speed of sound in a perfect gas is strictly, entirely proportional to the square root of its absolute temperature.
Nothing else matters.
Nothing else matters.
Right.
Not the ambient pressure, not the density,
Yeah.
just the temperature.
Let me make sure I grasp this. If I am in a room at sea level, and it's a comfortable 16 degrees Celsius, the speed of sound is roughly 340 meters per second.
Correct.
If I take a highly pressurized chamber at sea level, pump it up to 10 times atmospheric pressure, but keep the temperature exactly at 16 degrees Celsius, the speed of sound is exactly the same.
Exactly the same. Because while you increase the pressure, the density increased proportionally, and those two effects cancel each other out perfectly.
Wow.
The only thing that determines how fast those molecules can pass the bump of a sound wave to their neighbor is how fast they're already vibrating, and temperature is just a measure of that vibration.
Hotter molecules are zipping around faster, so they transmit the wave faster.
And colder molecules are sluggish, so the wave travels slower.
So when a commercial airliner climbs up to 30,000 feet, where the air pressure is incredibly thin, it's not the lack of air pressure that changes the speed of sound.
No, it's the fact that it is freezing cold up there. In the freezing upper atmosphere, the speed of sound drops significantly. This is why engineers don't typically measure high-speed flight in purely miles per hour.
Right, they use the Mach number, named after Ernst Mach.
Exactly. The Mach number is incredibly simple. It's a ratio. M equals U divided by A. You take the object's actual velocity, U, and you divide it by the local speed of sound, A, in the exact environment it is flying through.
So if the object's velocity is equal to the speed of sound, the Mach number is exactly 1. So a plane flying at a constant 500 miles per hour on the deck, right above the ocean, might be flying at Mach 0.6 because the air is warm and sound travels fast.
Right.
But if that exact same plane maintains 500 miles per hour and climbs to 40,000 feet where it's 30 below zero,
Because the local speed of sound has dropped due to the cold, that same 500 mile per hour speed might now be Mach 0.8. The plane is much closer to breaking the sound barrier, even though it hasn't actually accelerated.
okay, this brings us to a phenomenon that is absolutely crucial to understand before we can talk about building jet engines or rockets.
The sound barrier itself.
Right. What physically happens to the air as an object accelerates toward Mach 1? I want to visualize this.
Let's use the Doppler effect to visualize it. Imagine a stationary object like a speaker resting on the ground, emitting a continuous tone.
Okay.
It is radiating sound waves outward in perfect concentric spheres. Like dropping a pebble in a perfectly still pond, the ripples spread out evenly in all directions.
I picture the ripples.
Now, put that speaker on a cart and start driving it forward. But drive it slower than the speed of sound, so the Mach number is less than 1.
The speaker emits a wave, moves forward a bit, emits another wave, moves forward, and so on.
Exactly. It's essentially chasing its own sound waves. The waves in front of the cart get bunched up, squeeze closer together. The waves behind the cart get stretched out.
That bunching up is the Doppler effect. Because the waves in front are squeezed tighter, the frequency increases.
Right, which is why, when an ambulance is driving towards you, the siren sounds higher pitched. As it passes you and drives away, the waves stretch out, and the pitch drops noticeably.
I have a specific way I've always liked to think about this to ground it in reality. I think of it like a traffic jam on a highway.
I like this. Walk me through it.
Imagine those sound waves radiating forward from the object are like the red brake lights of cars. If a car hits its brakes, the red lights come on. The driver behind them sees it and hits their brakes, and their lights come on. It creates a chain reaction, a warning signal traveling backward up the highway, telling all the cars, hey, there's an obstacle ahead, slow down, adjust your path.
That's a great visual.
When an airplane is flying subsonic, slower than sound, The pressure waves it emits act exactly like those brake lights. They travel forward faster than the plane, warning the undisturbed air molecules miles ahead.
They are essentially communicating with the air. They are sending a physical signal that says a plane is coming.
And because the air gets that advance notice, the molecules have time to smoothly part and flow gracefully around the shape of the wings and the fuselage.
The air is prepared. But now, let's accelerate our cart. What happens when the Mach number equals exactly 1?
The object is now moving at the exact propagation velocity of its own sound waves.
It's keeping pace perfectly. So it emits a wave, but it doesn't fall behind it. It rides right on top of it.
Yes. The waves can no longer escape out in front. Every single pressure wave the object emits forward stacks up perfectly on top of the previous one, right at the leading edge of the object.
It creates a formidable, intense wall of compressed air.
Returning to the traffic analogy, if you are driving your car faster than the brake light warning can physically travel up the highway, you outrun your own warning signals.
You slam into the stopped traffic ahead of you without giving them any prior notice to move out of the way.
You violently crash into the undisturbed air. And if you push even faster, if your Mach number goes greater than 1, you completely leave your waves behind.
You are constantly plunging into completely undisturbed, completely unwarned air. The air molecules don't have time to gently part. They are violently shoved aside.
And this abrupt, violent collision is what creates a shock wave.
Exactly. And what happens to all the sound the object is making?
Well, it can't go forward.
Right. Because you are outrunning your own waves, all those overlapping pressure spheres form a strict geometric shape behind you. It creates a cone. We call this the Mach cone.
The Mach cone.
The tip of the cone is pinned to the nose of the aircraft, and the cone flares out behind it. All of the sound, all of the pressure disturbances are completely confined to the inside volume of this cone.
That is wild. So if I am standing in a quiet desert and a supersonic fighter jet flies directly over my head at Mach 2, I literally will not hear it coming.
You will hear absolute silence as it approaches, and even as it is directly overhead. It isn't until the edge of that invisible Mach cone physically drags across your body on the ground that the sound finally reaches you.
And because all those compressed sound waves are piled up on the edge of that cone, when it sweeps over you, you don't just hear the engines, you experience a massive, explosive sonic boom.
Exactly. And the faster the jet flies, the sharper the angle of that cone becomes, right? It sweeps back tighter against the jet.
Right, there's math for that too.
The angle of the Mach cone, which we call alpha, is defined mathematically by sine alpha equals 1 divided by m. So at exactly Mach 1, the cone is flat. It's a wall.
But at Mach 2, it sweeps back to a 30-degree angle.
And at Mach 5, it's an incredibly tight needle shape.
So let's pivot here. If pushing an object through the air at high speeds creates these massive, violent pressure differences and shock waves, how on earth do aerospace engineers design things like rockets?
That's the million-dollar question.
How do you take hot, chaotic gas and intentionally force it past that sonic limit without it just blowing the engine apart?
That is one of the great triumphs of mechanical engineering. To understand it, we have to leave the comfort of standard, everyday fluid dynamics behind. We have to look at how pipes and nozzles handle supersonic flow because the rules are entirely reversed.
Okay, let's explore this. We are moving into the bizarre, paradoxical geometry of supersonic nozzles.
To set the baseline, we have to imagine a theoretically perfect scenario. We assume the flow of gas through our nozzle is isentropic.
What does that mean practically?
It means we are assuming a reversible adiabatic process. Adiabatic means no heat is being transferred in or out of the pipe walls. The gas isn't losing heat to the metal.
And reversible.
Reversible means there is zero friction. The entropy of the system, the fundamental thermodynamic measure of disorder and wasted energy, remains completely constant. The change in entropy is zero.
Okay, a magical, frictionless, perfect pipe.
In this perfect system, we have an unbreakable rule called the continuity equation. It simply states that the mass flow rate must remain constant. Matter cannot magically appear or disappear.
So whatever amount of massive gas enters the front of the pipe, that exact same amount of mass must exit the back of the pipe every single second.
Exactly. The mass flow rate, m, is calculated by multiplying three things: the density of the gas, rho, the velocity it's moving, u, and the cross-sectional area of the pipe.
Rho times u times a.
Right. If
Yeah.
you change one of those three variables, the other two must automatically adjust to keep the total mass flow rate identical.
Okay, I can visualize this using normal, everyday subsonic flow, like water coming out of a garden hose.
Let's use that. The water is moving relatively slowly, so the Mach number is far less than 1. It behaves just how your intuition expects.
If I have water flowing out of the hose and I want it to spray faster to reach the other side of the yard, I put my thumb partially over the opening.
You are decreasing the cross-sectional area of the pipe.
Right. And because water is incompressible, its density doesn't change. So to force the exact same amount of mass through a much smaller hole every second, the water has no choice but to dramatically increase its velocity.
Perfect. For subsonic flow, a decrease in area causes an increase in velocity. It is highly intuitive. But here is the massive counterintuitive twist.
Hit me.
If the gas inside that pipe is already moving at supersonic speeds, if the Mach number is greater than 1, the physical rules of the universe flip completely upside down.
How so?
In a supersonic flow, if you put your thumb over the end of the hose, if you decrease the area of the pipe, the velocity of the gas actually decreases. It slows down.
Let me pause you there. That makes zero logical sense. Why would making the hole smaller slow a speeding gas down?
It all comes back to our first topic, extreme compressibility. When a gas is moving that incredibly fast, faster than the speed of sound, and you suddenly force it through a tighter bottleneck, the gas doesn't smoothly speed up.
It compresses.
Exactly. The intense collision with the narrowing walls causes the gas to compress violently. The molecules just slam into each other.
So the pressure and the density absolutely skyrocket.
In fact, the math dictates that in a supersonic flow, the density of the gas increases at a much faster rate than the physical area of the pipe decreases.
Oh, wait. Let me think about the continuity equation. Mass flow equals density times velocity times area.
Right.
If the area shrinks a little bit, but the density absolutely explodes to a huge number, then to keep the overall mass flow equation balanced, the velocity variable is mathematically forced to drop.
You've got it. The immense spike in density essentially chokes the speed.
Yeah.
Squeezing a supersonic flow slows it down.
Which means if shrinking the pipe slows a supersonic gas down, to make a supersonic gas go even faster, you have to do the exact opposite.
That is the astonishing reality. To accelerate supersonic flow, to make it go faster, the pipe must actually widen. You have to increase the cross-sectional area.
That is so deeply counterintuitive to my brain. If I take my thumb off the garden hose, the water slows down to a trickle. But for a supersonic gas, making the exit wider is the accelerator pedal.
It's wild, isn't it?
How did engineers ever figure out how to harness this?
It was figured out in the late 19th century by an engineer named Gustave de Laval working on steam turbines. He invented what we now call the convergent-divergent nozzle.
The de Laval nozzle.
Right? It is arguably one of the most elegant, pivotal pieces of engineering in human history. It is the iconic hourglass bell-shaped nozzle you see on the back of every rocket engine that has ever gone to space.
Okay, I want to walk through exactly how this bell shape works, from front to back, step by step, because the geometry feels like a magic trick. We start at the top, right at the combustion chamber of the rocket.
Inside that chamber, you have incredibly hot, highly pressurized gas from burning rocket fuel. But crucially, inside the massive chamber, the gas is moving relatively slowly. It is subsonic.
Okay, so as it flows out of the chamber, it enters the first half of the hourglass shape. The pipe starts to narrow. This is the convergent section.
And because the gas is currently subsonic, it behaves normally. Just like your garden hose, the narrowing area causes the gas to accelerate. It gets faster and faster and faster as the pipe squeezes tighter.
Until it hits the absolute narrowest point in the middle of the hourglass. Engineers call this the throat.
Right. And if the pressure inside the combustion chamber is high enough, something incredible happens precisely at that microscopic slice of the throat.
An absolute physical limit is reached.
Yes. The gas accelerates to exactly Mach 1, the local speed of sound. We call this the critical velocity.
And when a gas hits Mach 1 specifically at the narrowest throat of a pipe, it triggers a condition engineers call choked flow. What does it mean for a pipe to be choked?
It means the flow has mathematically maxed out. You cannot push any more mass through that hole. At the throat, the pressure of the gas drops to a very specific fraction of the original chamber pressure.
We call this the critical pressure, or P star, right?
Yes. For a standard gas like air, that critical pressure ratio, P star divided by P naught, is a fixed constant, 0.528.
So the pressure at the throat is always just over half of whatever the pressure is in the main chamber.
Exactly. Once you hit that critical pressure ratio and the gas achieves Mach 1 at the throat, the nozzle is completely choked. And here's the crazy part. Once it's choked, you could alter the environment completely, and the mass flow rate won't change.
What do you mean?
You could take the exit of that nozzle and expose it to the vacuum of deep space. You could drop the outside pressure to absolute zero, and the amount of gas moving through that throat will not increase by a single solitary gram.
I am struggling to understand why. If I hook a vacuum cleaner up to a pipe, it sucks more air through it. Why doesn't the immense infinite vacuum of space physically suck the gas out of the rocket faster?
It goes back to how fluid knows what the environment is doing. The information that there is a vacuum downstream, that suction, is physically transmitted backward through the gas in the form of a pressure wave, a sound wave.
Okay, so the vacuum tries to send a signal upstream saying, hey, it's empty down here, flow faster.
Yes, but that signal can only travel through the gas at the local speed of sound. Meanwhile, the gas itself is physically flowing downstream through the throat at the exact speed of sound.
Oh my God, it's like a salmon trying to swim upstream against a waterfall. If the waterfall is falling at 20 miles an hour and the salmon can only swim at 20 miles an hour, the salmon stays perfectly stationary relative to the shore.
It is exactly like that. The pressure signal trying to report the vacuum conditions can never physically swim past the throat. It is swept downstream as fast as it tries to propagate upstream.
That's brilliant.
Therefore, the combustion chamber is completely, blindly isolated from whatever is happening past the throat. The chamber has no idea the vacuum is there. The throat limits the flow absolutely.
That is a phenomenal piece of physics. But here's the problem. A rocket needs its exhaust to leave the engine much, much faster than Mach 1 to generate enough thrust to overcome gravity. If the throat limits it to Mach 1, how do we get more speed?
This is where Gustave de Laval's genius comes in. Immediately after the narrow throat, the nozzle begins to gently flare outward. The pipe lightens.
This is the divergent section, the bottom half of the hourglass, the big bell shape you see on a space shuttle.
And because the gas is already traveling at exactly Mach 1 when it enters this widening section, our paradoxical supersonic rule kicks in.
Exactly. The gas is now supersonic. So the gradually widening area of the bell doesn't slow the gas down like it would in a garden hose.
Instead, the widening area allows the gas to rapidly, violently expand. The density plummets. And to satisfy the continuity equation, as the density drops, the velocity is forced to absolutely skyrocket.
The gas expands and accelerates to Mach 2, Mach 3, Mach 10, shooting out the back and generating massive, world-shaking thrust.
When you step back and look at the bigger picture, you have to admire the profound elegance of this.
Yeah.
We are not using complex, moving mechanical pumps to force gas past the sound barrier. There are no moving parts in a nozzle.
Just geometry.
We are simply manipulating the stationary, physical geometry of a piece of metal to trick a hot gas into breaking the laws of intuition. We are exploiting the mathematical quirks of density and pressure ratios to send humanity into orbit.
It is absolute design perfection, but nature usually doesn't like it when we push things to the absolute limit.
No, it doesn't.
What happens if our perfect geometry meets the messy real world? Like a rocket engine is designed to expand gas to a specific pressure. What if the atmospheric pressure outside the rocket doesn't perfectly match what the nozzle is expecting?
That leads to highly violent consequences. The gas hits a wall. And this is where we have to explore what happens when supersonic flows fail and how shock waves are formed inside machinery.
Let's dive into that. We've got this beautifully smooth supersonic acceleration happening in the divergent bell of our nozzle. But what if the back pressure, the actual pressure of the atmosphere pushing back against the exit of the engine, is too high? Say the rocket is still on the launch pad at sea level where the air is thick.
If the back pressure from the atmosphere is too high, the gas inside the nozzle overexpands. It drops its pressure too low during its acceleration, and suddenly it finds itself pushing against a wall of thick atmospheric air.
So it hits a literal wall of air.
Yeah, the supersonic velocity simply cannot be maintained against that heavy resistance.
So it has to slow down.
Yes, but fluid dynamics dictates that a supersonic flow cannot just gently, smoothly decelerate back down to subsonic speeds. It can't just ease off the gas pedal. It has to slam on the brakes.
Oh, boy.
And the way a fluid slams on the brakes is by spontaneously generating a shock wave right inside the divergent bell of the nozzle.
Wait, it generates a sonic boom inside the metal engine itself.
It does. The gas is cruising along at Mach 2. It hits this invisible threshold of atmospheric resistance, and instantaneously, across a microscopic distance, it drops to subsonic speeds.
That sounds incredibly destructive.
It can be. As a rocket climbs through the atmosphere and the outside air pressure changes, this internal shock wave will actually migrate up and down the inside of the bell.
Let's clearly define what this shock wave is physically, because it's not just a loud noise. Earlier, we said a normal sound wave is a tiny, gentle pressure disturbance. What is a shock wave?
A shock wave is a macroscopic pressure discontinuity. It is a massive, incredibly violent step change in the state of the gas. Imagine a wall, roughly a few micrometers thick.
Okay, picture a wall.
On the upstream side of that invisible wall, the gas is moving at supersonic speed with low pressure and relatively low temperature.
Yeah.
The instant the gas molecules pass through that micrometer-thin wall, the velocity plummets to subsonic. The pressure spikes violently and the temperature absolutely skyrockets.
It's like the gas is running full speed into a brick wall of its own making. And does a shock wave travel at the speed of sound, like a normal noise?
No, this is another key difference. A normal sound wave always travels at exactly the local speed of sound, regardless of how loud it is. But a shock wave is different. A shock wave actually travels faster the larger the pressure rise is across it.
So a bigger explosion creates a faster shock wave.
Exactly. If a bomb goes off, the initial shock wave rips outward much, much faster than Mach 1. But as it expands, it loses energy, the pressure difference drops, the wave slows down, and eventually it decays into a regular sonic sound wave that just sounds like a distant boom.
I was looking at the math that governs this brutal transition. There is a set of relationships called the Rankine-Hugoniot equations. Now, I am not going to pretend I can solve nonlinear differential equations in my head, but conceptually, what do these equations fundamentally prove about how shock waves behave?
The Rankine-Hugoniot equations are the definitive map of a shock wave. They precisely correlate exactly how pressure, density, and temperature on the front side of the shock relate to the backside.
Right.
But the most profound revelation hidden inside these equations comes when you look at the entropy calculations.
Entropy being the measure of disorder or wasted heat in a system.
Right. The math lays out an absolute ironclad rule of physics. A shock wave can only develop when the upstream flow of the gas is supersonic. It is physically, mathematically impossible to generate a shock wave in a subsonic flow.
Why is it impossible?
Because the equations show that if a shock wave were to form in a subsonic flow, it would cause the total entropy of the system to decrease. And according to the second law of thermodynamics, in an isolated system, entropy can only increase or remain constant. It can never go backward. The universe forbids order from spontaneously forming from chaos without adding outside energy. Therefore, the universe forbids subsonic shock waves.
That is mind-bending. The physical geometry of our universe requires you to be breaking the sound barrier to create this phenomenon. Now, these shock waves aren't just flat walls, right? They take on different shapes depending on what they are crashing into.
Yes, the references distinguish between normal and oblique shock waves.
Let's talk about that.
A normal shock wave is the simplest type. It stands at exactly 90 degrees perpendicular to the flow direction. It's a flat wall. You typically only see normal shocks contained inside pipes or hovering right in the throat of a jet engine intake.
Okay, what about an oblique shock?
An oblique shock wave happens at an angle.
Like the wake behind a boat, but in the air?
That's a great visual.
Yeah.
Imagine a supersonic fighter jet. The nose of the jet is usually shaped like a sharp wedge or a needle. As that sharp point slices into the supersonic air, it deflects the air at an angle.
It can't compress straight back.
Exactly. The air compresses diagonally, creating an oblique shock wave that sweeps back from the nose.
The shape of the object doing the piercing really matters here, doesn't it? If the wedge angle of the jet's nose is sharp enough, the shock wave stays perfectly attached to the very tip of the metal. It slices the air clean.
It does.
But what if you try to push a blunt, fat object to supersonic speeds?
If the physical angle of the object is too blunt, if the metal curves away too steeply, the air simply cannot physically turn fast enough to get out of the way. The mathematical limit is exceeded.
What happens then?
When that happens, the shock wave actually detaches from the vehicle entirely.
It detaches. Where does it go?
It stands off in front of the object. It's called a bow shock, or a detached shock wave. It hovers a few inches or sometimes feet directly in front of the blunt nose, moving along with the craft.
Wow.
This creates a massive, violent zone of highly pressurized, extremely hot, subsonic air trapped right between the shock wave and the front of the vehicle.
Which creates incredible aerodynamic drag. This is why supersonic planes, like the Concorde or fighter jets, look like sharp needles. They want to keep the shock wave cleanly attached to minimize drag. Yes.
But on the other hand, look at the Apollo space capsules returning from the moon. They hit the atmosphere at Mach 25, and their heat shields were completely flat and blunt.
And that was a deliberate, genius engineering choice.
Because they wanted to stop.
Right. The Apollo capsule wanted to slow down. They wanted massive drag. But more importantly, by using a blunt shape to intentionally create a detached bow shock, that hovering layer of incredibly hot compressed air acted like a thermal buffer.
Oh, that's smart.
The most intense heat of reentry was concentrated in the shock wave standing a foot in front of the capsule, rather than directly touching the metal surface of the heat shield.
They used a wall of invisible compressed air to shield themselves from burning up.
That is brilliant.
Okay, so we've established that a wedge or a concave curve compresses supersonic air and creates a shock wave. But what happens if a supersonic flow goes around a convex curve?
What do you mean?
Like, what if the air is flowing fast over a flat surface and the surface suddenly drops away like a ledge? Does it create a reverse shock wave? It creates something entirely different and quite beautiful called a Prandtl-Meyer expansion fan.
An expansion fan.
Remember, a shock wave is a sudden, violent compression. But when supersonic flow goes around a convex corner, when it has more room to expand, it doesn't violently snap. Instead, it smoothly spreads out.
How does a fan work?
From the very point of the corner, the flow generates a fan made of countless, infinitely thin pressure waves called Mach lines, radiating outward.
Okay, so it curves around.
As the supersonic air turns around the curve and passes through this fan, it smoothly and continuously accelerates, expands, and drops in pressure. There is no violent shock, no sudden wall, no loss of total energy, just a beautiful, continuous acceleration around the bend.
Wow. Okay, so far we've been talking about these flows in a highly theoretical way. We assumed earlier that the flow in our nozzle was isentropic, perfect, frictionless, and retaining all its heat.
Which is never true in the real world.
Exactly. Real pipes are made of rough metal that causes friction. Real jet engines have intense fire inside them. How do we model reality?
That is where engineers rely on two highly specific models, Fanno flow and Rayleigh flow.
Let's start with Fanno.
Fanno flow is the mathematical model for a pipe where the flow is still adiabatic, meaning we assume no heat is passing through the walls, but we introduce the irreversible reality of friction. The gas is physically rubbing against the rough interior of the pipe, creating drag.
Okay, so Fanno flow is the math of friction. What is Rayleigh flow?
Rayleigh flow approaches the problem from the opposite side. Rayleigh flow assumes the pipe is perfectly smooth and frictionless, but we add intense, deliberate heat transfer.
Like in an engine.
Yes. This is the model used to understand what happens inside the combustion chamber of a jet engine, where burning jet fuel is constantly dumping massive amounts of thermal energy directly into the flowing gas.
Friction and heat. And the most mind-blowing thing about these two models is what happens when you plot them on a graph.
Oh, yes. The entropy diagram.
If you chart both Fanno flow and Rayleigh flow on a graph measuring entropy, they both do something completely bizarre.
They do. Whether you were dealing with subsonic flow or supersonic flow, whether you were applying friction or applying heat, both the Fanno line and the Rayleigh line naturally, inevitably curve and converge toward exactly Mach 1.
The speed of sound.
Yes. If you have a subsonic flow in a pipe and you add friction, the friction causes the pressure to drop and the flow to accelerate toward Mach 1.
And if it's supersonic.
If the flow is supersonic, friction causes it to decelerate toward Mach 1. The same is true for heat in Rayleigh flow. Adding heat drives the gas toward the speed of sound. Mach 1 represents the exact state of maximum entropy for that specific pipe.
It is like the thermodynamic destiny of the system. No matter what you do, the universe is trying to drive the flow toward the speed of sound, and once it hits that bottleneck of maximum entropy, it physically cannot go any further without changing the pipe itself.
It is a profound bottleneck in nature. The physics simply converge.
I want to pivot drastically here because this raises a major question for me. We have spent this entire time talking about gases, compressible, squishy, high-speed gases. But what happens when we look at liquids? We established at the very beginning that liquids, like water, act completely incompressible. They don't stretch, they don't squeeze, they are stubborn. So what happens if a heavy, stubborn, incompressible liquid suddenly undergoes an extreme pressure change?
When you subject an incompressible liquid to extreme dynamic forces, the liquid stops acting so polite. It becomes highly destructive.
This brings us to the chaotic, often violent world of unsteady flow and a phenomenon known as the water hammer.
Let's get into it. We are shifting our perspective from steady-state flow, which is smooth, constant, predictable movement, to unsteady flow, where velocities and pressures are rapidly changing over time.
Where do engineers actually deal with this in the real world?
Unsteady flow is everywhere. It is the core of any system that transmits power or provides automatic, precise control using liquids. Hydraulics.
Like construction equipment.
The heavy machinery on a construction site lifting tons of dirt, the flight control surfaces moving the flaps on a commercial airliner, even the hydraulic brakes in your car. All of these rely on unsteady fluid dynamics.
The foundation of this usually starts with a very simple, almost peaceful thought experiment. Imagine a clear plastic tube bent into a U shape and partially filled with liquid.
Right, a simple U-tube manometer. The water rests evenly in both vertical columns, perfectly balanced by gravity.
Now imagine you blow gently into one side of the tube, pushing the liquid column down on the left, which forces the liquid on the right side to rise.
And then you let go. You stop blowing. What happens?
The liquid column immediately falls back down, but its momentum carries it past the center resting point. It pushes the left side back up.
Exactly. The liquid will oscillate back and forth, sloshing from side to side, exactly like a pendulum swinging on a grandfather clock.
And what's amazing is that you can calculate the exact timing of that slosh using the same physics as a pendulum. The cycle time, t, equals 2 times pi, multiplied by the square root of L divided by 2 times g. It is pure harmonic motion.
It is. However, unlike a perfect pendulum in a vacuum, the water doesn't slosh forever. The liquid is rubbing against the walls of the plastic tube.
Right, friction.
This laminar frictional resistance steals a tiny bit of kinetic energy with every swing. It acts as a dampener. Eventually, the oscillations get smaller and smaller until the fluid settles perfectly back to rest.
Okay, so that's a gentle oscillation, but let's scale that up to industrial sizes. Let's look at what happens in a straight pipe.
Okay.
Imagine a massively long straight pipe connected to a huge water reservoir. There's a closed valve at the end. When you suddenly crank that valve open, the water doesn't just instantly blast out at its absolute maximum speed.
No, it takes time. In the very first fraction of a second after opening the valve, the entire head of pressure, the massive weight of the water sitting in the reservoir, is dedicated entirely to overcoming inertia.
Overcoming inertia.
It is applying force to accelerate a very heavy stationary mass of water residing in the pipe.
So it starts accelerating.
Yes, but as the water speeds up, the dynamic changes. Fluid friction against the inner walls of the pipe kicks in. The faster the water goes, the harder the friction fights back, stealing energy from the driving pressure.
It creates this smooth mathematical curve on a graph. A logarithmic curve.
Yes. Extremely fast acceleration at first, when the water is slow and friction is low, then the acceleration tapers off gently. It curves until the driving pressure from the reservoir perfectly balances the friction loss of the pipe, and the water achieves a final, steady velocity.
Okay, so opening a valve is mathematically quite elegant. It is a smooth transition to a steady state. Closing a valve, however, is an absolute nightmare.
The water hammer.
The water hammer. I think almost everyone has experienced this in an old house or an apartment building. You wash your hands, you turn the tap off quickly, and suddenly the pipes behind the drywall violently bang like someone hit them with a literal hammer.
Yeah, it's startling.
I want to break down the exact mechanics of a water hammer. Let's go millisecond by millisecond. You've got water flowing steadily down a pipe, and someone violently slams a lever valve shut. What exactly happens in that first instant right at the valve face?
In that very first millisecond, the physical momentum of the fluid right at the valve face drops to absolute zero. It hits a solid wall.
Bam.
But water is heavy. It has mass, and it was moving with velocity. It possessed kinetic energy. That energy cannot just vanish.
And because water is essentially incompressible, it cannot squish like a pillow to absorb the blow.
So where does the energy go?
It converts instantaneously into a massive localized pressure spike right against the metal face of the closed valve.
Exactly. The formula for this spike is terrifyingly simple and linear. dP equals rho times V times A.
So the change in pressure equals the density of the fluid, multiplied by its original flowing velocity, multiplied by the speed of sound in that specific fluid.
And here is where the chaos begins. That pressure spike doesn't just sit there. The water directly behind the valve has stopped. But the water 100 feet back up the pipe has no idea the valve is closed yet.
Because the signal hasn't reached it.
It is still rushing forward at full speed.
Yeah.
So that trailing water violently crashes into the stopped water. It compresses the water by a microscopic fraction of a millimeter and instantly stops itself.
It's a microscopic high-speed pileup, car after car crashing into the back of the jam.
Exactly. And as each layer of water crashes and stops, the high-pressure zone expands backward. This creates a high-pressure shock wave that travels physically upstream, moving backward against the original flow direction at the speed of sound through water.
Okay, so I am picturing this invisible wall of intense destructive pressure traveling at thousands of miles an hour all the way back up the pipe. What happens when it finally reaches the open reservoir at the other end?
When the shock wave reaches the open tank, the highly pressurized water inside the pipe suddenly finds itself open to the much lower, normal resting pressure of the reservoir. Nature hates an imbalance.
Oh, man.
So the highly pressurized pipe literally vomits the water backward into the tank.
The flow actually reverses direction.
It reverses. But this sudden release of water drops the pressure inside the pipe significantly below normal. Now you have a low pressure wave. And that low pressure wave travels all the way back downstream, back toward the closed valve.
And when that low pressure wave finally hits the closed valve, the water is trying to pull away from the valve face. It creates a suction.
A powerful suction.
That suction then reaches back to the tank, pulls fresh water from the tank back into the pipe, and the entire high-pressure slam cycle starts all over again.
It bounces. High pressure traveling upstream, low pressure traveling downstream, over and over again, bouncing back and forth.
That loud, violent banging noise in your walls is the physical shockwave ricocheting off the ends of the plumbing, vibrating the metal until friction finally dampens the energy away.
Now, you mentioned earlier that the speed of this destructive wave, the sonic velocity, depends on the fluid. But we have to factor in the real world here. Water isn't flowing through a magical, rigid vacuum. It's flowing inside a real physical pipe.
Right, a pipe made of steel or copper or concrete.
And under that immense, violent pressure spike of a water hammer, even solid steel is not perfectly rigid. The metal actually stretches.
It does. When that shockwave hits, the massive internal pressure causes the pipe to expand radially. It literally bulges outward slightly as the wave passes.
Right. And because the walls of the pipe yield and give way under the pressure, the volume of the pipe increases slightly. This makes the incompressible fluid appear to be compressible. It suddenly has extra room to give.
So the environment itself changes the fundamental math of the fluid. We can't just use the standard stiffness or bulk modulus of water anymore. We have to calculate a modified bulk modulus, K prime.
Right, a K prime that actually includes the elasticity, the Young's modulus of the solid pipe material itself.
We have to treat the water in the pipe as a single combined flexible system.
Correct. And because the pipe absorbs a significant portion of the shock energy by physically expanding, the velocity of the shock wave actually drops. If you have an ordinary steel or concrete water pipe, the wave velocity drops from the pure speed of sound in water down to roughly 600 to 1,200 meters per second.
Which is still incredibly fast, over 2,000 miles an hour. So how do civil engineers prevent this phenomenon from just destroying municipal water grids and industrial plants?
The simplest, most effective way is to just not slam the door. You use slow-closing valves. Engineers use a complex formula called Levi's equation to calculate the exact maximum pressure spike based on the closure time of the valve.
The goal is to stretch the physical closure time out to be longer than the time it takes the shock wave to make a full round trip up to the reservoir and back down the pipe.
Exactly. So if you close it slowly, the low-pressure reflection wave returning from the reservoir meets the high-pressure wave still being generated by the closing valve, and they destructively interfere.
Yes, the waves essentially cancel each other out, bleeding off the kinetic energy safely and gradually, rather than in one catastrophic spike.
I want to make sure we understand the real-world stakes of this. This isn't just about avoiding an annoying banging noise in your apartment walls. Think about a massive industrial hydropower station built inside a mountain.
Okay, picturing it.
The stakes are absolute life and death. A large hydropower station uses a giant, heavily reinforced pipe called a penstock. This pipe funnels thousands of tons of water down a massive vertical drop directly into a spinning turbine.
Wow, okay.
Now imagine a worst-case scenario. The electrical grid suddenly drops its load, maybe a substation blows out. The turbine suddenly has no resistance and it starts overspeeding. If it spins too fast, it will tear itself apart.
So the safety systems have to immediately choke off the water supply to save the turbine.
But if those massive multi-ton penstock valves at the bottom of the mountain are commanded to close too fast, the resulting water hammer wouldn't just make a noise.
It would be a bomb.
The kinetic energy of thousands of tons of falling water instantly converting to pressure would easily exceed the yield strength of the steel. The pressure spike would literally explode the penstock right out of the side of the mountain, flooding the facility and causing a catastrophic failure.
That is genuinely terrifying. The invisible forces hidden in moving water are immense.
Okay, I want to take a step back and look at where we are. We have equations for perfect gases in perfect nozzles. We have equations for single shock waves traveling up straight pipes.
Simple shapes.
But real-world fluid dynamics is almost never a straight pipe. It's turbulent, chaotic air tumbling over a swept jet wing, or chaotic water violently spinning in 3 dimensions through a curved turbine blade.
It's messy.
Trying to calculate valve leakage, irregular pipe friction, and 3-dimensional interacting shock waves by hand is just impossible, right?
It is fundamentally mathematically impossible to solve by hand using the governing physics equations, which are known as the Navier-Stokes equations.
Why are they unsolvable? What makes them so uniquely difficult?
Because the Navier-Stokes equations are deeply nonlinear. In almost all practical intermediate flow regimes, you have two competing forces. You have the inertia term, which is the forward momentum of the fluid, its desire to keep moving in chaotic directions.
Okay, inertia. And you have the viscosity term, which is the internal friction of the fluid, the stickiness that tries to smooth the flow out. Because inertia and viscosity fight each other in incredibly complex, nonlinear ways, a change in one intimately changes the other in unpredictable loops. There are no analytical pencil and paper solutions for complex shapes.
Which perfectly sets up the final act of our masterclass, teaching computers to see the flow. Because we could not solve the math by hand, humanity had to invent an entirely new field of engineering.
We had to invent computational fluid dynamics, or CFD.
Mm.
Since we cannot calculate a single elegant equation that solves the entire volume of fluid holistically at once, we had to find a workaround.
And what's the workaround?
The solution is something called the finite difference method. Instead of looking at the whole, we discretize the fluid. We break the continuous flowing mass of air or water down into a highly structured mathematical grid, or a mesh, made of millions of tiny individual boxes.
I love comparing this to the evolution of photography. Back in the day, theoretical fluid dynamics was like an analog photograph. You were trying to capture the entire continuous image in one single holistic chemical exposure, one giant math equation.
That is a highly accurate analogy.
But CFD is like a modern digital camera sensor. Instead of looking at the whole picture, CFD breaks the universe down into millions of tiny independent pixels or cells.
And the magic happens inside each individual pixel. To figure out what the fluid is doing inside one specific box, we use a mathematical trick called Taylor series expansion.
Explain that simply, if possible.
Essentially, Taylor series expansion allows us to take those impossible, curvy, nonlinear partial differential equations and approximate them into simpler straight-line algebraic equations that a computer's processor can actually solve.
Okay.
We calculate the basic velocity and pressure in one single cell, and then we pass that result across the boundary to the neighboring cell. The computer solves every cell, and then refreshes the entire frame thousands of times a second to simulate the passage of time.
And there are different mathematical strategies for how you pass that information between the cells, right? The literature mentions forward difference, backward difference, and central difference.
Yes. Let's look at central difference. If a computer wants to know the rate of change inside a target cell, central difference looks at the cell immediately behind it and the cell immediately in front of it and averages them. It looks at both neighbors.
That seems like a smart way to do it.
It provides what we call second-order accuracy, meaning it is highly precise and captures fine details. However, it has a fatal flaw.
Which is?
If you're simulating flows with very high Reynolds numbers, meaning very fast, highly turbulent, chaotic flow using central difference, can actually cause the entire simulation to become numerically unstable.
Unstable how?
The tiny rounding errors between the cells amplify, bounce back and forth, and the math literally explodes to infinity. The simulation crashes.
So how do software engineers fix a crashing simulation?
They switch to a technique called the upwind difference method. It relies on a very simple physical truth. In a highly fast, rushing flow, almost all the relevant physical information is coming from upstream, blowing down toward you.
What happens downstream doesn't really affect you.
Exactly. So the mathematical formula intentionally weights the upstream cells much heavier than the downstream cells. By favoring the upwind data, it suppresses those chaotic mathematical oscillations and keeps the simulation perfectly stable, even at extreme speeds.
Okay, so that is how we build the grid and keep it stable. Now let's look at how we actually simulate physical events inside that digital space, starting with incompressible fluids, like water. There is a historic landmark breakthrough in CFD called the MACE method, or marker and cell method. Why was it so revolutionary?
The MAC method was developed specifically to solve a problem that plagued early computers, simulating free surfaces. Imagine trying to simulate water sloshing in a half-empty tank or a wave crashing on a beach.
That sounds incredibly complicated.
It is. The boundary where the water meets the empty air is incredibly complex to track mathematically. In the MAC method, the computer generates the background mesh, but then it drops tens of thousands of weightless marker particles into the simulated fluid.
What do you mean by weightless?
They don't have mass, they don't affect the physics equations, they're essentially digital dye. They're just dropped into the mathematical current, and they simply track exactly where the fluid physically exists within the grid as the velocity and pressure equations push them around over time.
Okay, so if a cell has markers in it, it's water. If it's empty, it's air.
Right.
I remember seeing the visual they used to prove this method worked, and it is iconic. They used the MAC method to simulate a single liquid drop falling into a shallow puddle. We have all seen that famous high-speed macro photograph where a milk drop hits a surface, and the splash violently forms a perfect, symmetrical little crown of liquid spikes shooting upward.
Yes, the coronet splash. It is a highly complex, chaotic, three-dimensional physical event.
The MAC method, using a primitive computer from decades ago, was able to perfectly simulate the physics of that crown forming, spike by spike, droplet by droplet, purely by tracking those weightless marker particles through a grid. It proved that computers could replicate the chaotic beauty of fluid nature.
It was a triumph. But as impressive as the MSc method is, what is truly fascinating is how much more difficult the math becomes when we switch back to our first topic. Compressible fluids. Supersonic air. You can't just track velocity and pressure with digital dye anymore.
Because of the shock waves.
Exactly. Shock waves are violent discontinuities. To simulate them, the computer is forced to solve the equation of state and the energy equation simultaneously with mass and momentum. The temperature and density are wildly, violently fluctuating from cell to cell.
So how do supercomputers compute a shock wave without crashing?
We use what are called time marching methods. A prominent example is the McCormack method. It is incredibly useful because it uses conservation forms for mass, momentum, and energy. But to save massive amounts of computational power, it temporarily ignores the viscosity of the air. It treats the air as frictionless.
So it's a simplification.
Yes, but this method is brilliant and highly efficient for predicting macro-level aerodynamic events, like calculating exactly where a detached bow shockwave will form a foot in front of the nose cone of a supersonic rocket.
It paints the big picture. But what if the big picture isn't enough? What if you need to calculate the viscosity? What if the microscopic friction of the air rubbing against the metal is the whole point of the engineering problem?
When you need absolute granular reality, you have to step up to the heavy artillery. You use something like the IAF method, the implicit approximate factorization method, which is also commonly known as the beam warming method.
Okay, the beam warming method.
This is heavy-duty mathematics. It does not take shortcuts. It solves the full, complete, viscous, compressible Navier-Stokes equations.
Where would an engineer ever need that much punishing mathematical detail?
Look inside a modern commercial jet engine, a turbofan. Imagine the massive titanium fan blades at the front of that engine. They are rotating at thousands of revolutions per minute. At those rotational speeds, the tips of the blades are actually breaking the sound barrier, while the base of the blades near the hub are moving subsonic.
So the air flowing through the fan is this nightmare chaotic mixture of subsonic and supersonic flow at the exact same time. Transonic flow.
Precisely. And in that transonic environment, microscopic shock waves are constantly forming, detaching, and interacting with the turbulent friction boundary layer right on the curved surface of the metal plates.
That is intensely complicated.
It is. The beam warming method, running on parallel supercomputers, can physically map that incredibly complex density distribution. It allows engineers to literally see the friction and the microscopic shock waves rubbing against the titanium, allowing them to tweak the curve of the blade by a fraction of a millimeter to save millions of dollars in jet fuel.
It is almost godlike. The ability to take the invisible, chaotic, destructive forces of nature forces that would rip a building apart and map them out in perfect digital color on a monitor.
It's an incredible time to be an engineer.
Okay, as we wrap up this masterclass deep dive, I want you to give us something to chew on. We have covered a massive amount of ground. What is the ultimate destination of all this physics and computer science?
I think you just have to look back at the incredible journey we just took. We started with scientists in the 1800s playing with sealed boxes, realizing that pressure times volume equals temperature. just the basic rudimentary relationship.
Right.
And we trace that intellectual lineage through supersonic rockets, through exploding water pipes, all the way to supercomputers calculating three-dimensional friction on a rotating jet turbine. Here's the provocative thought for the future. As computing power marches relentlessly toward quantum levels, the mathematical pixels in our CFD meshes will become infinitely small. We might soon reach a point where we can run fluid dynamic models so perfectly precise, so indistinguishable from reality, that physical wind tunnels and metal prototypes become entirely historical relics.
You mean never building a test model again?
Imagine an aerospace engineer designing a next-generation supersonic aircraft. They can test every single physical parameter, stress the metal against virtual shockwaves, and fly the plane for thousands of simulated hours in every weather condition imaginable, entirely inside a silicon chip before a single piece of actual metal is ever cut on a factory floor. We will transition from reacting to the physical world to generating it perfectly in code.
That is profound. Designing and perfecting reality in the digital realm before it ever physically exists. Well, design junkies, that brings us to the end of our masterclass on the invisible forces around us. If you haven't already, give us a like and follow, and please leave us a comment if you enjoy the podcast. We love to hear from the folks who make this possible.